All right, okay. Yeah, hello, I'm Jan van den Brandt. I'm going to talk about multi-commodity flows and how that kind of relates to graph techniques. Let's start with some basic definitions. First, what is a single commodity flow? So this is just the basic flow problems that you all know. Things like max flow or min cost flow. You're given some directed graph with edge capacities, maybe also some costs. You have a source and target vertex, S and T, and you now need to route a flow in this network. And this here, for example, would be a maximum flow, right? It routes the maximum amount of flow from S to T without violating these capacity constraints. So this would be a single commodity flow because you just have one kind of commodity, one kind of stuff to route in this flow, just this blue unit of, let's say, water. Okay. Now, two commodity flow would be when you have more than one commodity to route. So here we have a second pair, S and T. And now we need to have two flows in this network, but they still share the same capacities. And important here is that everything that starts, let's say, at the blue source S must reach the blue target T. So it's not okay to, let's say, start some flow at S and then it reaches the green T. So that's not allowed. You need to have specific pairs between S and T. All right, so this is two commodity flow, and of course you can also generalize this to K commodities where you have K pairs of source and sink. And there are different variants of this problem. I'm going to focus here on the high accuracy regime, by which I mean the solutions here are allowed to be fractional flows. So I don't need to have integers on these edges. That allows me to actually solve this in polynomial time. So if you want to have an integer solution, it becomes NP complete. That's going to be a bit tricky, so let's look at fractional solutions. Next, I allow for approximate solutions, some kind of 1 plus epsilon error. And here I want that I have so-called high accuracy algorithms, which means that the complexity is supposed to scale in log 1 over epsilon. So I don't want to have some kind of polynomial dependency, something like 1 over epsilon squared. That would be bad. Instead, I want to have something that's like log 1 over epsilon. Yeah, question?
Does the capacity constraint is over all commodities?
The capacity is over all commodities. So if you have basically the sum of all flows on any one edge must satisfy the capacity, yes.
So if you have polylog 1 or epsilon dependence, then why don't you get the exact answer?
Right. So if you have something that's really badly conditioned, you might actually need epsilon to be exponentially small in order to round to the optimal solution.
Here means what in this context? Like in multi-commodity flow, it's like if they are integers bounded within polynomial in n, do you ever...
Right, like if we assume every integer is, on the capacities, is bounded by some polynomial in n, then typically it's enough to have epsilon something like 2 to the minus n to round to an exact solution. But that is kind of the worst case. We're fine with approximate solutions, so let's say epsilon is some polynomial. That's kind of the regime that I'm going to look at here. Yeah. All right. So that's multi-commodity flow and the high accuracy regime. Another problem I'm going to look at are linear programs. So of course, you can use linear programs to model your flow problems. So linear program, right, says minimize some linear cost function subject to linear constraints. And that can model flows because what you can say is something like, let's say, two commodity flow. Every flow that goes into a vertex must also go out. So we kind of have the sum of the flows that goes into a vertex minus everything that goes out is supposed to be 0, except for the source and sink pair. And we have that for both flows. And we also want that, okay, both flows together satisfy the capacities on the edges. And that f is positive really just means that, okay, on your directed graph, you really need to satisfy the direction. Okay, so we have some obvious hierarchy here, right? We can say single commodity flow, that's easier than multi-commodity flow. In multi-commodity flow, you can phrase that as a linear program. So you have this hierarchy when it comes to how hard these problems are. And now let's look at some algorithms. The best upper bounds are single commodity flow, almost linear time, really efficient. Something like linear program, one of the fastest algorithms runs in matrix multiplication time. So here omega is the matrix multiplication exponent. That's the complexity of multiplying two m by m matrices. And now for multi-commodity flow, we have something that's in between these two upper bounds. And yeah, it turns out that, okay, both of these flow problems, they are based on this framework of using some continuous optimization method, some kind of linear programming optimization routine, and combining that with graph techniques, graph data structures. You've seen the talk yesterday, right, where it was outlined how this gives you some kind of fast single commodity flow algorithm. Today I'm going to talk about multi-commodity flow. And the first thing I want to explain is why it's actually really surprising that you can use graph techniques for multi-commodity flows. So let's start with that. Let's look at the history of multi-commodity flow. So very early, there was some polynomial time algorithm. And well, polynomial doesn't really mean that it's efficient. So one of the first sufficiently efficient algorithms is by Kamaka. So he invented the central path method for solving linear programs. And well, multi-commodity flow can be phrased as a linear program. So you get this m to the 3.5 complexity for solving a multi-commodity flow to high accuracy. And since then, a whole bunch of improvements were made, but all of these improvements are faster linear program solvers. So each of these improvements is just a faster LP solver, and well, you can apply that to multi-commodity flow. You get a faster multi-commodity flow algorithm, but really, these are not, technically they're not multi-commodity flow algorithms, right? They're linear program solvers that you just run on the LP that reflects multi-commodity flow. Okay, so no real multi-commodity flow algorithms for this high accuracy regime. And that's actually really different for single commodity, right? We have that all of these optimization techniques could be combined with graph-specific ideas that give you algorithms that are really efficient for specifically single commodity flow, not just linear programs in general. Things like Laplacian system solvers, or maybe some kind of graph decompositions like the expander decomposition and so on. All of these graph-specific techniques could be used together with continuous optimization to get these fast single commodity flow algorithms. But somehow, that did not happen for multi-commodity. We could not use any of these graph techniques to get faster multi-commodity flow algorithms. It's really just linear program solvers. So why is there this distinction between these two? Why does it look like multi-commodity flow does not support graph techniques? So it was kind of asked before. There is some evidence for this, why it's kind of reasonable to not expect graph techniques. One thing is that, let's say you want to solve it exactly, multi-commodity flow. Ita' back in the 70s has shown that any linear program can be reduced to a multi-commodity flow instance. So if you have an exact multi-commodity flow algorithm, you immediately get an exact linear program solver. And now recently, Rasmus has, with this group, they have extended this to this high accuracy regime. They've shown that any linear program, you can reduce that to a two-commodity instance. So that means any algorithm that solves two-commodity flow to high accuracy, that is actually a linear program solver. Right? You can solve linear programs with any high accuracy multi-commodity flow algorithm. So that kind of explains why only linear program solvers give you these two-commodity flow algorithms. But it also gives some intuitive idea for why graph techniques couldn't really help. Because think of it, right? You have a linear program. Maybe that linear program does not have any kind of graph structure. Why would you expect graph techniques to now be useful to solve this linear program more efficiently? If you would get a faster two-commodity flow algorithm using graph techniques, wouldn't that imply you now have a faster LP solver using graph techniques? That seems unintuitive, right? Because maybe there is no graph structure in the LP. Why would you use graph techniques then? But it turns out that all of these reductions create sparse graphs. So you can very well create some algorithm that works on a dense graph, is more efficient on dense graphs and uses graph techniques, and it doesn't really imply anything for LPs. So maybe there's actually a way to now use graph techniques on these denser graphs, and we show that's actually true. On dense graphs, you can get a more efficient multi-commodity flow algorithm using these graph techniques. So kind of what we're showing is that, at least on dense graphs, multi-commodity flow seems to have more of a combinatorial, more of a graph-theoretic structure than we previously thought. So let's summarize this here. previous algorithms, right, they were all just faster linear program solver, just new algebraic techniques, new optimization techniques, no graph ideas that were going into these high accuracy algorithms. And now we get the first result that actually uses graph techniques, and it's for dense graphs, because all of these hardness results, they were really only for sparse graphs. Okay. So questions so far before I go to the next part, which is a bit more technical. What are the graph techniques that we used? Okay. Yes?
It's interesting that you write like hardness results suggest improvement only via faster LP solvers. Is there a trend of trying to improve sparse to commodity flow to get faster LP solvers? Are people doing this at all?
I'm not aware of that. No. So, I mean, I'm also saying suggest here because, right, formally it's a reduction, and that doesn't really prove that it's impossible, right? It's really just this intuition that you wouldn't expect graph techniques to help for LPs. So it's not, this is really just a suggestion, right? It's not a formal proof of graph techniques are impossible. Yeah. And I'm going to actually get into that a bit more later, that maybe we could actually use graph techniques to get faster LP solvers. Okay. All right, so data structure problems, graph techniques, what are we using here? I did not start a timer. What's the time?
You have 15 minutes.
15, okay. So I'm using a framework that's called the central path method. So since this is kind of a graph theory workshop, I'm not going to talk too much about these optimization routines. Let's just say that the central path method, in a sense, you can think of that as a reduction that says, given a linear program, if you want to solve that, instead you can just look at a sequence of linear systems. And these sequence of linear systems, it's slowly changing. So from one iteration to the next, it's almost the same linear system, only a few changes. And that motivates the use of data structures, some kind of dynamic algorithm that returns just a solution to your linear system. And in previous work, kind of two main data structure problems were identified. One is called matrix inverse maintenance. That's, as the name suggests, is a really algebraic thing. So let's not focus on that here. Let's focus on the other problem called HeavyHitter problem. And for many linear programs, it's actually this HeavyHitter problem that's going to be the bottleneck. So let's quickly define HeavyHitter problem. What kind of data structure problem do we have to solve here? So here you're given a matrix, A. It's kind of a tall matrix. So let's say this box here represents your matrix. And the data structure task is to preprocess this matrix. Try to figure out some useful properties. And after you're done with the preprocessing, you get a bunch of queries. So you get a bunch of vectors h and some threshold t. And whenever you get one of these vectors, what you have to do is you need to return the large entries of this matrix vector product. You don't have to compute the entire matrix vector product. That would be rather slow. Just tell me what are the large entries of it. And if you can solve this efficiently, then you get faster linear program solvers. So this really is the main bottleneck. Major open problem is that we have no idea how to solve this for sparse matrices. We have something that's optimal if the matrix A is dense, but for sparse matrices, we have no idea how to solve this efficiently. So kind of an open problem is, given a sparse matrix, let's say k non-zeros per row, can you preprocess that? Oh, I didn't specify what m is. M is the height of the matrix, this larger dimension here. That's m. Can you preprocess that in m times some polyterm, the number of sparsity, the number of non-zero entries per row, such that then every query, the complexity is roughly proportional to some polynomial in k and L, where L is just the number of indices you're going to return. So if there are few large entries, you spend only little time. If there are many large entries, you spend a bit more time, but it's supposed to be just proportional to kind of the number of entries you're going to return and something that is polynomial, small polynomial in the number of non-zeros. Yeah?
So is T here dependent on any norm of the vector AH?
T here is, so what's going to happen is that basically every 2 to the I iterations, T is going to be 1 over 2 to the I. So sometimes, well, most often T is like a small constant, but less frequently you might also use a higher accuracy for this threshold.
But it is
Right, so it's different in the sense that online matrix vector really asks you to get the entire output, the entire matrix vector product. And here, we only need the large entries.
But if T is on, that's the same thing.
That depends on your matrix and the vector, right? I mean, let's say I have a 1 and a -1 somewhere, and maybe the vector h has like a 1 and a 1.1, then the result would just be 0.1, right? So right, this does not have to be a 0-1 matrix and a 0-1 vector. Yeah. It's just anything over the reals. Yeah. All right, so this is the main bottleneck. And it turns out that all of the provable hardness for linear programs and so on, and the provable hardness for multi-commodity flow, that's actually all in this matrix inverse maintenance. At least currently, there is no evidence that you shouldn't be able to use graph techniques for this heavy hitter problem here. And, well, matrix vector product, it often has some kind of graph structure, right? Like a matrix vector product, that's a bit like, let's say, one step of random walk, for example. So there's often some graph perspective of what a matrix vector product is. So maybe you can actually use graph techniques to solve this heavy hitter problem. So open problem, we don't know if that's true. At least for the special case of multi-commodity flow, we can use graph techniques to make this heavy hitter problem more efficient. Okay. So I can talk more about this during the open problem session. All right, so what's the idea for solving this more efficiently in the case of multi-commodity flows? So in the special case of multi-commodity flow, what we have to do is we have to solve this problem on something called a k-commodity incidence matrix, if we have k commodities. Let's define what that is. So let's say this is our matrix A, and let's just focus on one row. Let's say for now it's a regular incidence matrix. And a regular incidence matrix just has a +1 and a -1 in every row, but if it's a weighted graph, you're really just having some plus weight and minus a weight per row. Now, for a multi-commodity matrix or incidence matrix, what you have is that basically this is not one row, it's more like a block of k rows. And the edge weights that you have is actually some small k by k sized matrices. So every edge now has a weight, but the weight is not just a number, it's a small matrix. So you end up with some kind of block matrix where every consecutive k blocks kind of have this more incidence matrix structure with weird edge weights. In particular, for multi-commodity, that's a sparse matrix with some kind of 2k non-zero entries per row. So it's kind of a special case of this open problem that I stated earlier. All right. So we are going to solve this by showing that this can be reduced to classic incidence matrices, and then we're going to see incidence matrices you can actually use expander decomposition, some graph theory techniques to solve this more efficiently. Okay. So how do we reduce this to incidence matrices? So we have our multi-commodity matrix. You can kind of reorder the matrix a bit, right? So here I have basically an incidence matrix, but every entry is a k by k block. Now I can say, just by reordering, I can say these are k by k many blocks, but every entry is an incidence matrix, right? Just reordering rows and columns. Basically, if I just, for every edge, take only the top left entry, that would be the top left block up here. And you just do this for all the entries of your weights to get these blocks. So when I reorder the columns, I can also reorder h a bit. So what this allows me to do is basically split this into smaller problems. Right? Instead of asking, is maybe one row multiplied with this vector, does one row have a large entry? Well, a row could have a large entry if maybe any one of these small terms has a sufficiently large entry. Right? So if I detect just all the entries where one of these smaller incidence matrices with one of these smaller vectors is larger than t over k, then I know, okay, no, the other way around. If there was a large entry here, then I know at least one of these small ones must have had an entry larger than t over k. All right. So I'm definitely going to find all the indices that are large entries, but I might actually detect too many. Right? It could be that maybe this first b with the first h is a really large positive number, but this last b and the last h is a really large negative number, I detect these large entries down here, but they happen to cancel, so I shouldn't even have to return that entry. So maybe I'm returning way too many indices, and just writing down that index in memory, that takes time. So if I return way too many indices, that's going to slow down my entire algorithm. So I need to bound how many entries I'm actually going to return here. Now, I can describe how we do it, but I don't have a good intuition for why it works other than one page of calculations. So what we do is we kind of reorder things a bit. So you can prove that the spatial structure of this multi-commodity matrix gives us that any sum of these matrices here, if you sum them along one row, that gives you 0. That allows you to rephrase this sum as the sum of differences between two h vectors. Right? You're taking the sum over hj, so this hl is always multiplied with this b, and the sum over the b is equal to 0. So this term here is just going to add an extra 0. It doesn't change anything. But now, if I look at large entries in any one of these terms here, somehow that does not result in cancellations, or only in very few ones. So more formally, what we prove is that if I look at the norm of any one of these small products, and I just take the sum of these norms, note that if there's a large entry, then the norm must be large. So having a bound on this norm tells me how many large entries I might detect. And you can show that actually this absolute value, you can kind of move that outside. It's like a page of calculation just to show that it works. I don't have a good intuition for why it works other than read the proof. But it shows that, right, basically the number of entries that are going to be large is only going to increase by like a constant factor. I'm not going to return too many because, well, if there were large entries in here, then the norm would also be large, and the norms are roughly the same. Okay, so we can split the task of HeavyHitter on multi-commodity matrices to HeavyHitter on regular incidence matrices. What is the time for that? 4 minutes, okay. Then let's quickly outline why this is a graph problem. So we have this problem, incidence matrix B, maybe some kind of edge weights as well. These are now regular scalars, and we want to have that if you, let's say, put the scalars on a diagonal matrix. So this weighted incidence matrix times h, tell me all the large entries of this product. Since this is an incidence matrix, what we're really saying here is we're given a weighted graph G, and I want to return all the edges where, for a given set of like potentials on the vertices, the difference between the two endpoints is larger than my threshold. Right? This is exactly the same problem because an incidence matrix had just a +1 and a -1 per row. Okay. So now we have this graph perspective, and we can now use the expander decomposition on this. Let's start with a very stupid algorithm that doesn't work and see why expanders fix this issue then. Naive algorithm. Well, let's assume for simplicity the graph is unweighted. I don't have weights. Asking, is the difference larger than t? I could ask something like, okay, is any one of the two endpoints larger than t over 2? Right? If one of the endpoints is larger than t over 2, then maybe the difference could have been larger than t. But again, I might be returning too many entries. It could be that the two endpoints are both larger than t over 2, but the difference just happens to be 0. So again, I might be returning too many entries. And so this algorithm doesn't work, but on expanders it works. We'll see why. So let's say we use this expander decomposition that we have seen on Monday. You have your graph, split it into expanders, and on an expander there's this nice property that if you take the sum over the vertices for some given vector, you weight the entries by the degree and you add up these squares. As long as your vector was orthogonal to the vector of the degrees, you can bound this by this expression. What does this tell us? So let's say we take our trivial algorithm. We look at one of these GI, one of these expanders. Remember, we wanted to look at entries where the difference is large. So I can just add an all-ones vector onto my h. That's not going to change the difference because both endpoints are going to be added or subtracted by the same amount. So I can just add this so that h becomes orthogonal to the degree vector. And now I just say, okay, for every vertex, just check if one of these endpoints here is larger than my threshold. If yes, just return every edge that's incident to that vertex. And that's basically the trivial algorithm from before, except for this extra shift by the all ones vector. But now it works because how many entries are we going to return? We're going to return the degree of that vertex, many edges, whenever this h was larger than our threshold. So whenever this ratio here is larger than 1, we are paying this degree in like time to return all the entries. Now if you look at the sum, that's basically exactly our expression here. And we know it's an expander thanks to the expander decomposition. So you can bound it by this expression. So that's the weights with the differences of our endpoints on each edge. But that is precisely an upper bound on how many entries would we have to return, like how many entries are larger than t, than our threshold. Right? Whenever this fraction here is larger than 1, we would have to return that entry. So we're not going to return too many entries using this almost naive algorithm. Okay. So the summary here is that this HeavyHitter task on multi-commodity incidence matrices can be reduced to regular incidence matrices. That can be seen as a graph problem. You can use things like expander decomposition to solve that efficiently. And that's kind of the first time we managed to use graph techniques to get a faster algorithm for this high accuracy multi-commodity flow. And open problem is this HeavyHitter problem, can we solve that on a more general class of sparse matrices? Maybe we can even use graph techniques there because all of the provable hardness of linear programming is kind of in this other data structure problem about something with inverse matrix and so on. Just this task of matrix vector product, it might be that graph techniques could actually be helpful here. Okay. Thanks.
Do I understand correctly that you still return too many indices, but only a constant vector or something, so you can actually check all of them?
Right. So like you return, it's technically a polylog vector, but yes, we return a few too many entries, but you can just check them. Yes. Yeah. Yeah. So as long as you're not returning too many indices, everything works out. Yeah.
Okay, let's thank Jan again.